I would like to know, are you able to hear me clearly or not? I mean, am I audible? This is just to check whether the chat is going on properly or not, because now we can access or we can see your chat. So my first question is, are you able to hear me, or is there an issue? Okay, I have one yes from Ashish. Okay, okay, I'm audible. Okay, so the second thing I wanted to point out before we go forward is that these sessions are crucial for your AI and maths understanding, or maths related to AI understanding, and they go to a certain level of depth. Now, I know some of you are first year, we are aware of that. Some of you are, of course, second year. But the point is that, the markets today and the need of AI engineers today is so big and so intense that these things you need to pick up quickly. I know I have had some people telling me that, some of these ideas are new, some of these ideas are uh, probably a little difficult to understand in the beginning, but the reality of the situation is that you need to understand. I mean, there is no other way. So what I would recommend is that, as you're listening, perhaps a few terms maybe not new to you. We'll try and elaborate as much as we can, but there will always be some things which will be new to you. It happens to me also when I read stuff. My submission to you would be, when you find something new, just make a note of it. Anyway, the lectures are recorded and available. I hope you are able to access them, and we can then you can use ChatGPT, because we have to focus on ChatGPT as a mechanism to understand, substantiate what I'm saying. And please get into that habit that you don't understand a term or you want to read up more on it. Make exhaustive use of ChatGPT like tools, Claude, ChatGPT. Those are the tools I use. I do use some of the Gemini also, but mainly I use Claude and ChatGPT. Please make use of these tools so that you understand things much better than what I have covered in the class, or maybe substantiate them more. You should do that, because the part of this program will be to also help you understand how to maneuver or learn to learn. And we can give you these guideline lectures, but after that you need to prepare. Now, having said that, my next question to you would be, uh, uh, yeah, today we are going to go a little more deeper into the theory. Today also we are not going to do any practical. We are going to do only theory, because you need to understand matrix multiplication really well, and how is it done in a naive manner, and how is done in a GPU. So I'll be giving you a little insight into how GPUs work. Now, some of you will think GPU is too early for us to get into. Well, the fact is, no, it is not early at all. AI is all around us, and it is time to get yourself immersed into AI. My job is to make that journey as smooth as I can, but I will not be able to make that journey very smooth unless you are prepared to make an effort to do that. Only then the journey will become smooth. So I will pause here and ask you another question. So, are you in the last class we discussed matrix multiplication, if you recollect, uh, and the naive, the stupid way of doing matrix multiplication, and we also, and I'm going to summarize it again a little bit now, but have you understood the naive way of doing uh, the matrix multiplication, the naive or the stupid way of doing matrix multiplication? I'm going to say it again briefly, but I just want to know whether you have kind of understood that. Okay, so I'll pause for a few minutes to listen to you, and then we will continue to listen to your answers. No, I think you have to scroll. Okay, somebody says he understood it. Yeah. I have some responses from Muhammad Abdul Mukeet. I also have something from Ashish. There's a bit of a lag, I guess. Okay. One more time. Yeah, I'm going to summarize it briefly. Okay. Okay. I think I will now go ahead and do a brief summary. I always start a session with a brief summary of what we did in the last class so that you have a context. But I am hoping that you will, read up based on the access to the recording we have. They are accessible, isn't it? Yeah. So the recordings are available, and we can ask that also. Are you able to access our recordings of the previous lectures? Are you able to access our recordings of the previous lectures? Just say yes if you are able to access. Just say can access. 20
seconds delay will be there.
Yeah, I know. Ah. Okay, the recording and the lecture notes are both accessible. Fine. So I think thank you, Abdul. You, because see, giving the feedback is as important as being able to do that. Uh, yeah, somebody's saying I would appreciate something. How can we access? Oh, okay. How do we access? See, this is the issue. How do we access?
We share a link in the group, sir. They have to click on the link and see the recordings directly.
Apparently, we have sent a link to you in this group. You have to click the link, but they should be accessible somewhere also, no?
It is open all the time. I can keep it as a.
No, it should be accessible through some portal, right? That's normally the way anybody would access. See, some site to which they go and access.
You can go to the group description. No need to switch between the sites.
Currently, I think the URL is available in the group to which all of you have access to, and it is available from there. Okay. Yeah, somebody is able to say he's able to access. Okay, fine. So I think it's time to get us started. So I'm going to start with a brief summary of what we did last class, and then we are going to take it forward. There was another confusion. This session is only up to 12 o'clock, not up to 1 o'clock. It's 10 to 12. We just want you to keep you for 2 hours, not more than that. Okay. So last week, we looked at the problem of matrix multiplication. And also, I told you a brief about why matrix multiplication is so important for AI. I think I will start with that very quickly. So we said in AI, we have a lot of input data. Uh, which we have to process, and that input data we normally call as X. Okay, and if you remember, we had represented X as a set of attributes, and we had represented the neural network as a set of layers, which we called hidden layers. We said this is hidden layer 1, hidden layer 2, and so on. And then there would be an output somewhere here. And we said in nowadays in networks, these hidden layers are in thousands. And this is the input. This is just one row of input. Normally, this input is multiplied by some W, and then it goes to activate these units. These units are called neurons, which again activate using some other weight. Let's call this W1, this is W2, and so on and so forth. So this is the input, gets multiplied, because this input may seem like a column, but at one shot we normally deal with a batch of inputs. So there is a batch of inputs that we normally see. So given this batch of inputs, basically we process them. That is called X, and processing them means multiplying this with W1, and then normally we add a bias term also, and then multiply it with W2, and so on and so forth. And then we do some loss computation, back propagation, but we are going to come to that slowly. Right now I'm only focusing on just this part, the multiplication part, the multiplication of X. X is a matrix and W is a matrix. And basically we are talking about the multiplication of X and W. X by into W is what we are focusing on, and that gets multiplied. Let's call this W1, gets multiplied, becomes something else, and goes on. So that is what we had talked about last class. And we talked about this matrix multiplication, and we said that in every AI platform, it is this multiplication which takes a hell of a lot of time. And why is that? Imagine that we have a batch of, let's say, 100 items of data. Let's say our batch is of 100 items of data. And let's say in X is about 10 attributes. Each X, that is the data that we are dealing with. So if it is a blood pressure data, remember I gave you the example of diastolic, systolic, the amount of the amount of blood flow, the amount of weight, gender, family history, all of that. So I gave all those attributes. Let's say for simplicity, let's say there are 10 attributes like that. So this X is a 100 into 10. Again repeating, how did I get 100 into 10? Each row of data or each sample of data or each patient data is about 10 attributes. And we are dealing with 100 at one shot because we want to process a lot of data. So 100 into 10 would be the size of X matrix. This is into, so let's put a star there. And then the weight matrix depends on how many neurons you want activated there. More the number of neurons, the more smarter is the network and more costlier is the network. So let's say there are 200 neurons there. So if there are 200 neurons, then I need to have a W2 organized as a 10 into 200 kind of a matrix, right? So there will be from each one of them, there will be 10 and 200 such neurons will be there. This is 200, and for each one, I'll have 10 weights. So this is that 10 and 200 neurons, right here, and this will go on. So just to do that, what will be the number of multiplications that I'll have to do? So this is M, this is K. We normally refer to this as K. This is also called K, and into N. This is the way we normally refer to. So the number of multiplications which will have to be carried out are M into N into K. That is the number of multiplications which will have to be carried out. I'll give a little more justification about this, but so many multiplications have to be carried out. And so many multiplications in our case will mean 100 into 200 into 10, which is 2 into 10 power 5. That is almost 2 lakh multiplications will have to be carried out. And I also remember telling you that multiplication is a slow operation, and that's why we need dedicated hardware to enable us to do multiplications at a rapid rate. So 2 into 10 power 5 multiplications just for one iteration, one epoch as they call, and then we go further and further and further as a deeper network. So remember, if you have 1,000 layers and this for only one layer, you will have 1,000 times the same kind of calculation. Just to give a rough idea, which will be for one trip through the network, you will have 2 to the power of 2 into 10 power 8, almost zero point 0.2 billion multiplications you will have to do for just one iteration of one batch of data. And imagine there will be thousands of samples of data, millions of samples of data, and you will have to do this repeatedly. So you can imagine why it becomes a gargantuan problem, that it is not possible to address this problem with the standard our CPU based problem, CPU based solution. And we will talk about why that is not possible, and we will take it from there. Okay, so I am now going to go a little more further. This we have already discussed in the last week presentation, and I hope at least some of you have absorbed or grasped the presentation of last class and absorbed it. Now we will go forward and understand a little more about the CPU GPU conundrum, and also understand how these multiplications are coming. Okay, so now we are talking about matrices. So basically we have an M into K matrix. So let's say this is an M into K matrix. Let's say it's a 3 into 2 matrix. This is M, this is K. And the second matrix, which is the weight matrix in our case, is K into N matrix. So this is a K into N matrix. This is typically our weight matrix. So this is our second matrix, and we have to multiply this two matrices. So this is, let's say, 2 into maybe 4, or maybe let's make it 2 into 3 again, a matrix. So the result of this is going to be a 3 into 3 matrix. Okay, so 3 into 3 matrix. So let's draw a 3 into 3 matrix. That is going to be a result. So normally in literature we call this A, we call this B, and we call this C. I mean, when we write programs, we call this A, B, C. But we know this is nothing but the result of the multiplication of the input matrix X with the weight matrix W, and giving us the first level answer. So that's what happens here. So this is C. So we initially zero out all the 9 elements. Why did I say 9 elements? Because 3 into 3 is 9 elements. So initially, when we are doing the multiplication, we put all 0 elements here. All 9 3 by 3 rows are all 9, and then we start computing each element. How do I get each of these elements? Let's spend a little time understanding how do we get this element. Again, I have discussed this at length in the last session. So in order to get this element, what do I need to do? I need to take this whole row from A, the first one, and multiply it with this column, right? So unless I multiply this row with this column, I won't get the answer. Which means, what I need to do? How many multiplications do I have to do? No. How many elements are there here? 2. How many elements are there here? 3. How much is this? 3, right? So in order to do this, how many multiplications, just to get one value of this, how many multiplications you have to do? Each row, this row, which is consisting of 2 columns, has to be multiplied with all the rows here, all the values in this column. There are 2 rows. This is 3 into 2. Yeah, sorry, this is 2 rows. There are 3 columns and 2 rows. Okay, so there are 2 rows. So each of these 2 columns has to be multiplied with these 2 rows. This with this, and this with this. This has to match. So this value has to be multiplied with this value. This value has to be multiplied. So this and this have to be multiplied. This and this have to be multiplied. So basically, to get each value, we have to do about k squared multiplication, right? In this case, am I right? There are going to be k squared multiplication for getting each of this value. We have to do so many multiplications. Let's keep that aside. You have to do a lot of multiplications for getting from here to here. This row has to be multiplied with this column. So that many multiplications has to be done, and of course addition has to be done to get the value. And then same thing we have to repeat. How do we get this? We have to get this row and multiply it with this column, and then we have to get the first row and multiply it with this column. Then we'll get this element and this element. So we have to keep doing this. So so for each element we have to do so many multiplications and get the values. So many multiplications and additions and get the values. And this has to be repeated 9 times, 3 into 3 times. This many for each one of them we have to do this operation. And that is where we waste a lot of time doing this. This row has to be multiplied with this row, and again this row has to be multiplied with this row to get this, and all that. Okay. Now this is what happened, was the standard way multiplication used to happen. And obviously there used to be a high number of multiplications which had to be done, because each row of the first has to be multiplied by each column, and then we will get the values and then we move forward. So you can say that the number of multiplications is a huge number. Okay, and this is all to get that value. Now people started thinking. So this is the naive way of doing things, right? And we saw the algorithm for doing that also. I will now digress. Again, this has been done earlier. We're just doing a catch up here, just to put up in context. I normally don't spend so much time in catch up, but knowing that you are first year, second year, I am doing that. So now let's look at the naive Python code which we went through last time, and see how did we do this using the naive algorithm. You remember we did something like this. No, you're right. You're at the right point. Yeah. We need
This one.
this is there. Yeah. Okay. Good. So you can see what we did. So initially, it doesn't matter if you don't understand the Python. See, there is another thing I will like to tell you. Now, code will be created by AI. See, it's not so important to understand or get lost in the syntax of code. You are going to be an engineer 4 years later, right? Most of you, some of you 3 years later. Now, when you're going to do that, even today, many people don't write code any longer. What you need to understand is what is happening in the code. That reading code, I will tell you, has become far more superior to writing code. Now, that doesn't mean you should know how to write code, but I'm just saying that reading and understanding, now code is going to be generated by systems. But if you have to use the code generated from AI or anywhere else, you will have to have an appreciation of what the code is. Or not that too, not line by line, but in general you will have to know what the code is doing. And that is super important, because here you may be writing code for agriculture, you may be writing code for healthcare, you may be writing code for drug discovery, you may be writing code for drones, you may be writing code for robotics. All of that you'll have to understand what is being generated. If you don't understand, you can't use it. Okay, it's like that. It's not, the generation used to be the focus for your earlier batches, for the last, when I was growing up, when even people were becoming engineers even 2-3 years ago, writing this code used to be a big issue. Now writing this code is no longer an issue, but able to comprehend the thing which is happening in this code is very important. For example, this code is generated not by our friend Nagi Reddy here by hand. He has used a tool and he has generated the code. So that's how it is going to happen. So you have to understand, for example, what is this doing? So you have to understand the language. Yeah, what is this doing? This is creating a two-dimensional array, because you see this outer square bracket is for the outer dimension, and there is one more inner square bracket for inner dimension. And what is the dimension of that matrix? It is an m into n matrix. Why am I saying m into n? Because you see, for each value in the range of m, for each, you read this as each, for each value in the range of m, which means 0 to m minus 1. How many values are there? 0 to m minus 1, m values are there. So for each value in range m, so it's building like this. It is taking each value, it is going creating row by row. So it's now creating the 0th row. For 0 in, it is going to create the columns. 0 for each number in the range n. N is the number of columns. So the columns are from 0 to n minus 1. This is how the number of columns are mentioned. So he is putting zeros here. Okay, he's putting zeros here. This is because of this 0. Okay, so now this is how C is getting created. So how many, what will be the dimension of C? This will be 0 to m minus 1. So this is m dimensions. And this is 0 to n minus 1. So this is n dimensions. So you say m into n. This is what C is getting created. Correct? Okay. So now we have created a empty matrix of m into n range, initialized with value 0. We call this initialization with value 0. This is what has happened. Now for I in range m, that is go through each row. This is the outer loop. This is the outer loop for each row. For j in range n, for each column, you're going row wise and column wise. Some value equal to 0. This is some kind of variable it is being used to set this value. For k in range k, he is doing, aik into bkj. He is multiplying those k values. So there are k multiplications happening here, right? K multiplications which are happening here. Because I think I said k squared. K squared is not the thing. K squared values are being multiplied, but the number of multiplications happening are k only. So aik. So if you see two matrices, remember I talked about the two matrices. Okay, this is A. This is the first matrix. Okay, this row has to be multiplied by this column. This row is getting multiplied by this column. So how is that happening? See, I am taking the first row and I'm going to multiply it with this column, all the values in this column. How many values are there in this row? K. How many values are there in this column? So they are 1 to 1 matching. So each value is getting matched and that value is going to come here. Okay. And then what am I going to do? I'm not going to change my m. I'm going to still stay in the same row. And now for each value of n, n is the next column, I am going to again do this row. So this second row is getting multiplied, second column is getting multiplied by this row. So this row stays as it is, get multiplied by this, and I get this value over here, whatever this value, right? And then I get this value. This is my first row will be done of the answer. And how many multiplications have I done there? K multiplications. You see there? For I in range k, because k multiplications have to be done. Why k multiplications? Each value here has to be multiplied by each value here. Then each value here has to be multiplied with each value here. So like that, k multiplications. So there are k multiplications. So the total number of multiplications happening here are, and after every resetting, I am setting it back to Cij is equal to some value. I am resetting. After all the multiplications are done, then I am filling up the Cij matrix, right? So this is how, and returning C. So this is a naive multiplication, and number of multiplications are m into n into k. That's how we counted. Remember in the beginning, there are m into n into k multiplications. Okay. So this is what is the basic theory that of naive multiplications that we do. And I gave you the maths. You know, if you have to do these many multiplications just for one iteration through thousands of layers, you will need about 1 billion or close to 1 billion multiplications. And if you have to do for millions of samples, you can imagine how many zeros I would need. You will need a huge number of multiplications to be carried out. And these multiplications will increase the complexity, and it will take years by the time the AI loops run and some answer comes out. So we should be able to improve that. And that is where our focus of today's discussion will start. Okay, so is this kind of clear? Because if you have appreciated this naive multiplication, then only you can appreciate the complex multiplication, or not complex, the you have to appreciate the challenge of AI. This is the challenge of AI. And perhaps, as I explained in the last session, this is the reason why NVIDIA, which brings in its GPUs, which can do multiplication better, and how we will talk about today, why GPUs will do this better and how they will do it better. We will talk in the next 1 hour. But now I'm going to just take a small poll just to see whether you are on the same page with me at this stage. Because if you don't get me at this stage, I and you both have a serious problem.
So what should be the polls?
Do a poll. Have you understood naive multiplication? Yeah, we're waiting for your answers to the poll.
It's 82.
Okay, I think we are at 73%. I think
Voted for
more or less over, right?
86% totally voted out of
Okay.
250.
No, more than that won't vote. They will find it difficult to vote and click and all. Some of them have difficulty with figuring out what is a poll and clicking and all. They're not that complicated. They find it very complicated. Okay, fine. We are ending the poll. It's about 73%, as you can see on your screens. 73% are okay with naive, and some have understood partially, about 25%, and some are no. We leave the no's aside. See, we have to move ahead. So my suggestion is, anyway, this is recorded, and I think the link is given to you. If not, we'll repost the link today of where we are having all these lectures. I think you're right. We should have them on some site. Because last week was all Dashra. We couldn't move our sluggish team to do much. This time I will do it this week, and we'll have it accessible. We'll put it on a portal, and then we will give you. I don't know whether it's already on a portal, but we will put it on a portal if it is not there.
Recordings.
Recordings.
No,
It's already on a
it's
portal.
on channel.
Okay.
It's go to channel.
Hmm.
But
Acha, it's on a go-to channel. Okay. Fine. So you have the
soon
link.
we will post in the KMIT Vista
I
channel.
think we should post it on KMIT Vista or something.
Yeah.
Yeah. We'll post it on KMIT Vista. I think that is the easiest. This week we'll put it on KMIT Vista, which is a YouTube based channel which we use. So we'll put it there, and I think be done with it. So that we create a separate group there, separate course there on KMIT Vista, and do it, and that's it. Okay, so it's going to be KMIT Vista, and you'll have YouTube accessibility, and so it will be open. Okay, so I think we will move on and help you now understand why the whole world has shifted because of matrix multiplication from a CPU to a GPU. So we are now entering it again, since once K range is, somebody was asking about K range. K range is the K multiplication. Uh, K is the common number. See, K is the number of rows in the first matrix and number of columns in the second matrix.
Number of attributes, dimensions.
Or in our problem, it is the number of attributes in the X, the number of features that we would like to record about X. That is also K. Okay. Okay. So we will range K means because we need K values, no? That is why the code has that K range, range K. That is, go through all the values of K from 0 to K minus 1. We need K values, no? Because see, we have to do K multiplication. So that many values have to be computed together. Okay. Okay. So we are now going to shift to the major discussion now on CPU to GPU, where I'll invest the next 1 hour and hope that you understand, but you will have to keep your eyes alert and minds even more alert. And some of it will still not make sense at the end of this session. I would really request you and urge you to look at ChatGPT, use my lecture as a touch base or a context point, and then go deeper and understand it, because that will give you a good grip on how GPUs work, how CPUs work, what are the limitations and all that kind of stuff. Okay, so I'm going to take a digression and now venture into why matrix multiplication is such an important thing, and why GPUs do it better, and how they do it better, and how is the architecture of GPU oriented towards that. Okay. Now I'm going to spend a little while on this slide, but with a little more insight, and then we are going to figure out something in more detail. Okay. Now a little more insight on how this is happening. So I'm going to again draw two small matrices and show you what is happening here. So let's say A is a 3 into 2 matrix. So 3 rows and 2 columns. And let's say this is a 2 into 3 matrix. Real life matrices are much longer. It's basically because I am using the screen to explain, I'm making it small. So the first value, as you know, is computed by taking this 2 and multiplying them with these 2. And the K here is 2. This is the K, right? The common. So 2 columns of 1 row are multiplied by 2 rows, 1 column. This 3, yeah. This is 2 into 3, yeah. So this 2 is getting multiplied with this 2. This is 2 into 3. Okay. Now just look at this. Okay. Just look at this and think a little. Now you'll have to think, keeping some abstraction in perspective. While this multiplication is going on, while this row is getting multiplied with this column, just imagine what is the amount of idleness in the system. Now you see this column is idle. Imagine this column is just lying idle. There's nothing happening on this column, right? So while this calculation is going on, I want you to see and I want you to grasp there is a lot of idleness which is happening. When I say idleness, what I'm trying to say is lot of data which is already there, which is available, is not getting used. That is my definition of saying data is idle. It is just sitting around doing nothing. If you see this column or this column or this row or this row and all of that, you see they are doing nothing. They are all idle. They are just looking at what is going on. I want you to develop that perspective. This is getting multiplied by this. Fair enough. This is a little busy, and while this is a little busy, the rest of the data is just lying idle. There is no collision. Is just watching. These rows are watching, these columns are watching. Think of that. Think of that kind of a concept, that while this is going on, these guys are all sitting and doing gatta chutta, which is like, smoking away to glory, staring at what is happening. There's nothing else happening. Only this is getting multiplied by this, and that's it. The whole machinery is idle and not doing anything. Now, could I not, while this is going on, could I not do, or could some other guy not do something like this? Take this row and multiply it with this data. Can't somebody have done that instead of waiting for this to finish and then this to commence, then this to commence? In the naive algorithm, you see what's happening. You focus your attention on this. While this is going on, imagine right now I is 0, j is also 0, because it is the first row, 0th row, and first column. Okay, j is also 0. So this is going on, right? Now the rest of the data, this data and this column, there's nothing happening. This row and this column, there's nothing happening. So it is until I finish this operation, then only he goes from taking this row and multiplying it with this column. See, first he just computes this one value, right? This one value, which needs this row and this column. This row and this column goes to compute this, right? And while it is doing that, can't I do this also? Can I not compute this also? Right now, until I finish this, the attention doesn't go to this guy. Unless I finish this, I won't go here. Correct? Why the hell should that be the way things are? I can go here and do this, because what does it need to do this? It needs this row and this column over here. To get this value, it has to take this row and this column and get this value. To get this, it has to take this row and this column, and it will get this, right? So why doesn't it go ahead and do that? Why does it have to wait for this to finish before I commence this operation, or before I commence this operation? Why the hell should that happen? That is the moot question. Why should I wait for this operation to finish, and then start this operation? They have no interdependency. They have no interlocking amongst each other. This guy can happen independently and happily, while this guy can also happen, isn't it? I mean, why the hell are we waiting for this to finish? Once this finishes, then I pick up the next value of j, and once all the values of j finish, that means this row is finished, then I go and pick up the next row of the answer. Why should I do that? All of this, you remember how many values are going to be computed here? It's a 3 into 3 matrix. So 9 values are going to compute. Right now what is happening? All the 9 values are getting computed in sequential manner. That is the problem with this naive code. All the values are happening one after another. First this value, then this value, then this value, then this, and then this. This is all happening in a sequential manner. I hope you understand the word sequential. Sequential means one after another, like a cube. One after another. This value is first done, this value is done, this value is done. And to give you an analogy, let's say you are at a booking counter, and it's like having one counter and everybody queuing up on that counter and waiting for that counter to finish the one booking to finish for the next guy to do it. It is as like that. That is because we have limited counters. We have limited abilities to do this operation, right? So if I have this, so at this point, I want you to buy this idea that there is a huge amount of idleness in this whole operation that I just described. This naive algorithm is very idle. It is wasting a lot of time. It is sequential. It is computing this value, then going for this value, then going for this value. Though there is no dependency between this value and this value. While this is going on, I can jolly well do this. I can jolly well do this. I can jolly well do this. That is this computation. All these 9 computations that you see have no dependence on each other. Nobody says I have to wait for this to finish for this to begin. Nobody has said that, right? And it's just a matter of a little thought and a little advanced thinking that all these 9 operations are being done sequentially. Do you see this sequentially? Because unless I finish this, I will not pick up the next value. Unless I finish all those values, I will not iterate over this. So by doing this, I am wasting a lot of time. And especially if my matrices are big and I try to do these sequential operations, I will waste a huge amount of time. And the trick of the game is to do parallel operations. So you have to understand, what do I lose out of doing sequential operations, and why I should seek parallelism in my operations. That's very important to appreciate. So the reason I am saying this is sequential is the way the code is written. That's why I call it stupid code. I call it very, very dumb code, because it has obviously some limitations which have come because of the hardware. I have to do this very, very slowly. I have to do this one operation, then do the next operation, then do the next operation. It is like a malgadi, going one after another. And this is the sequential way of doing things. And they are very bad. They will take a lot of time. So they will one after another. Just imagine. Now, what should be done? We have to somehow figure out a way. The way is very simple. I just have to do this operation, and all these operations parallelly. If I'm able to do that, I am kind of done, right? I'm kind of achieved my goal, that I am able to do this operation. So if I can do 9 parallel operations, imagine the amount of time. Let's just do a time. Let's say each of these computation, each of this inner loop, that is this loop, takes, let's say, for the sake of assumption, let's say takes 10 units of time, right? This whole operation that is doing this multiplication k number of times, this into this k number of times, let's say takes 10 units totally. So how much is this whole thing going to take, this naive loop going to take? It's going to take 90 units of time, remember, because I'm going to compute this, that 10 units, then I'm going to do this, again 10 units, then I'm going to do this and 10 units, and so on and so forth for 9 values on the answer. So I'm going to take 90 units of time, okay, 90 units of time. Whereas if I were somehow to be able to do this parallelly, I will finish this whole work in 10 units of time, right? By the time each is over, by the time this is over, this will also be over, this will be also over. So at one go, in 10 units of time, I'll be able to finish this entire operation. So imagine I have a 900% saving of time, from 10 units of time to 90 units of time, or from 90 units to 10 units. I have 900% saving of time. I'm going from 90 units to 10 units. See the immense, 9 times I'm able to make it faster. The amount of time I'm able to make it faster. Okay, I want you to buy this idea first, that the first 2 ideas are there here. There is no interdependence between these operations of computing this, this, and this. First point. Second point, if I can do this parallelly, I have a huge saving in time. Almost 9 times my overall time will be reduced. 9 times. Okay, not 1, not 2. 9 times my time will be. This is the central idea of parallelism. I want you to take this idea first. So two things, I have to do each of these operation. Each operation, let's assume, take 10 units of time, and after that I have to take 90 units of time. Sorry, totally I'll take 90 units of time, and that is what comes to this. Okay, so yeah, so okay. Now, have you absorbed the difference between sequential operation and the benefit that I will get if I have to do this operation in a parallel manner? Have you absorbed that? Okay. Now, before I take a poll, I will ask you to absorb one more point. Let me make that point, and then I will take a poll whether you have understood all of that, because these are central ideas. And if you start understanding the central ideas at this stage itself, you will have a fantastic journey with AI, because AI is all about thinking like this and doing things faster, better, and in a very systematic way. Okay, so now I'll erase this screen and I will present my second idea. Uh, yeah. Okay, now let's talk about the second idea. Okay, first we talked about difference between sequential and parallel. Okay, now again I'm going to draw these two matrices, one next to another.
You want a blank screen here?
No, 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 this is perfect. I'm going to draw this screen again. Again, I'm going to take 3 into 2 and 2 into 3. Same thing, 3 into 2 would make it 3 rows, 2 columns, 2 rows, 3 columns. Yeah. Uh, yeah, and my answer is, as you know, 3 into 3. Okay. Now, think with me a little. To compute this value, what do you need? You need this row and you need this column. That's all. If you know an R, that is the row index of this row, and the column index of this column, then you can get this value. So you need this row index and this column index. Yes. So you need this R1 and C1 to do this computation. That's the only information that you need, because these matrices are available. Of course, you need the matrices, but in addition to the matrix, to just compute this value, what do you need? You need this row and this column, because this row will identify which rows, which values you are going to take from here, and which values are you are going to take. This column will identify which which values you are going to take from here, from the second matrix, right? Basically, you need the column index of this and a row index of this. So this is what you need. And okay, let's think further. To compute this value, what do you need? You need R1 and C2, isn't it? You need to just to do this, you need R1 and C2. By the same token, you need R1, C3. Just these two values, if you know, you can compute this value, because you know which values to pick up, which values to pick up here and multiply them and get that. Same thing here, same thing here. So if somebody were to come and whisper in your ear, this is the row, this is the column, then this operation, the computation of this operation, can happen completely independently of any other operation. This is just the two parameters you need. This is just the two, somebody has to just whisper these two values in your ear, and you can say, I can compute this. You don't need the whole matrix, right? You don't even need anything else. You just need the original matrix, and I mean, you just need access to this row and this column, and you're done. Same thing here and here, same thing here and here. Just these two values will take you to the answer, right? So there are only two parameters that you need to compute this. For here, you probably will need R2, C1, R2, C2, and so on, right? I think you get the picture. As long as I give you, or I can whisper in your ears, this calculation, this calculation, this calculation, this calculation, and all, they can all happen independently of each other, right? So if I can, so I have talked of two ideas. I've said what is the difference between sequential computation and parallel computation. That is one idea which we talked about. Then I also talked about the idea of sequential being much slower than parallel, and I told you why it is slower. Then I also just now highlighted an important point, that for each of these operations to occur independently of others, each of these operation needs, each of these parallel operation needs two parameters, which row and which column they are going to operate on. As long as I am able to supply those parameters to that particular calculation, it can proceed parallelly and completely independently of each other. These are the two central ideas that I'm going to take a poll on and ask you whether are you able to understand these two central ideas, the difference of advantage and why of sequential versus parallel, one idea, and equivalent idea of the point that each of these calculations are based only on two values, the row of one and the column of the other. As long as I supply that to you, we can do that. Okay, so that's the idea. So I'm going to pause here and take a poll, and just to understand whether you have figured out what this means, the central idea. Have you grasped these? Okay, so let's do a quick poll and check. You can erase this. Poll is, have you understood difference between sequential and parallel? And have you understood the difference between sequential and parallel? And the need for two parameters for doing each calculation, and the need of two parameters for doing each calculation.
Yeah, poll has been launched. Please take the poll.
About how much percentage voted?
78, sir.
78% have voted.
Out of which
70% seem to 70 of 78% have understood. Partly is about 27. Okay. Okay, I think See, we normally wait for only about 80% of the poll to be, because we normally presume that about 20% of the people who have logged in are pretending to have logged in and have gone to sleep. Uh, they're celebrating Jai Telangana and Dashera and all that. And well, I bless them with all happiness, and continue to celebrate, uh, because this is probably the only opportunity you will soon have to celebrate, because the world is going to get very tough, and unless you guys are ready to focus on all this, we'll have issues. Anyway, fine. We will continue with the rest. Now we come to certain very important ideas of the difference of we just talked about the difference between sequential and parallel, and how probably we also laid the foundation for parallelism to proceed. Now we will focus on the concept of parallelism in a very different way. Okay, now I'm going to show you a picture. Okay, and then I'm going to connect this with the idea of parallelism. I think this is a full picture.
Yes.
Nothing is cut. Okay. Okay, now this picture, just look at this picture very carefully, and I will try and highlight some of the things on the picture. This is the traditional CPU, and this is the GPU. Okay, graphical processing unit, the revolution. Now you will see DRAM is the dynamic RAM. People call it by various names. There's cache, there is control logic, all of that. Here you can see the cache is small, it is per processor. Control logic is also pretty small. We don't need so much of that. The same chip length, chip size is taken, and it is being redistributed. So the same screen real estate, or in this case, the chip real estate, is redistributed in a different way, that there is more of ALUs or more of processing that is happening. Okay, now let's this was the old architecture, old. Okay, and this is the new AI driven architecture, and our problem is that of matrix multiplication. Correct. These are called the cores. These are called the cores. Okay, this all this it's shown here, but these are called the cores. This is where the work happens. Okay, here where the multiplication happens by using this repeatedly, and all that. Okay, now you will see the problem, right? Now again I'm going to draw the result matrix, which is a 3 into 3 matrix, and I'm going to talk about each value computation, right? So what is the key or the stark difference that you see here? The number of processing units are very limited. You see here, the number of processing units are very limited. How many processing units you see here? 4. Or sometimes you have more than 4. You will have, nowadays, even if you take high-end machines, you'll have 32 to 48, maybe even more. Okay. Whereas if you see here, the number of cores, that is the processing units, the number of processing units, that is these green ones, is not obviously to scale, are in thousands. It's better depicted here. A GPU has thousands of cores, and CPU has multiple cores, maybe in less than even 64. That kind of cores it has in a CPU. And you have multiple thousands of cores, 72,000, 50,000, like that. Just to give you an idea, I may be not correct. See, the KMIT group has an A100 and will next month have H200s. These are even bigger machines. We will have between these two machines close to about something like I think I don't have an idea, but let's say something like 20,000 cores at one point available for compute power, for doing multiplications. This will be our power of our data center, which will be there. This is real. Okay, this will be available from next month onwards, because a lot of the students who are doing drug discovery and who are doing a lot of interesting work in different kinds of drug modalities, they need brute compute power, which is of such high dimensions that our in-house infrastructure, which is currently an A100 only, and of course we have several tens of GPU clusters, but they are not adequate. So we are getting two very strong H200 machines, and we will soon have immense compute power for driving our AI story. We are perhaps one of the few colleges or group of colleges in South India to have this kind of course. But that's mainly not just educational, because we do a lot of R&D, especially in the drug discovery space, which needs heavy chemical computations, in pharmacokinetics and dynamics, which is how a drug works in a body. So you have to have a huge power, huge and brute power to drive these multiplications. So we are going to have all of this, and this is thousands of cores. Now, how does this change the situation? Okay, I am going to now take an empty page and illustrate why this is so important, and why am I keeping on saying this, and how does this architecture change it. And then we're going to see how do we have to rewrite the code to harness from our naive algorithm to see our naive algorithm is suited to do this. Okay, and the smart algorithm that I'm going to talk about, the parallel algorithm, is what is required to do this. See, this is like a highway. Think of it as a highway. Okay, rather I would say an expressway. Let's call it, the current word is expressway, ORR or something like that. Now you have an expressway. So who is an expressway? You have, this is the expressway, right? And this is your regular road. Now, if you have an expressway, unless you reorient your code and write it in the expressway way, to harness this architecture, there is nothing that you are going to get out of it, right? You are not going to benefit anything. It is like, I call it the classic bullock cart on a expressway story. If you are given an expressway, you need to drive a Mercedes on it. There's no point driving a bullock cart on it, right? You are not using the expressway at all. You are not getting the speed. So this will give you the expressway. That is, will give you those many cores, those many processing units, which can all operate in parallel, right? Here only 4 can operate in parallel. Here thousands can operate in parallel. Thousands or millions can, thousands, tens of thousands can operate in parallel. But to use this expressway, you need to design your code also in a smart way. Otherwise, it will be a bullock cart on a highway syndrome, which is what we would like to avoid. We won't want that thing to happen. So I'm going to now talk about how this is all done and how is this done. Okay. So here, what is the problem? Okay, let's talk about the problem with the old architecture, which uses these naive algorithms. See, the problem here is I have very limited of processing power. I have these 3-4 guys, that's all. And I have to do how many things? In a simple case, 3 into 3. But in a so even to do this operation in a parallel way, I need how many cores? I need 9 cores, right? Even to do this very simple operation in a parallel way, right? Where while this is going on, this should also go on, this should also go on my result. If I have to do this, I need at least 9 cores, 9 processing units. And even if you see this GPU which I have depicted here, sorry, CPU which I have depicted here, how many cores does it have? It has only 4 cores. So even this kind of a tiny multiplication, it will not be able to do. Look at how stupid it is. Even if I have 4 cores available, even if I have to do this thing in parallel, I won't be able to do it entirely in parallel, right? Because in order to do it completely in a parallel way, I have to need minimum of 9 cores. Why? Because I have to do 9 calculations. Just that basic 2 into 3, 3 into 2 and 2 into 3 multiplication. I have to have 9 cores if all of them have to happen in parallel and simultaneous. Otherwise, there will be some amount of sequentiality which will automatically come in. So even a simple matrix multiplication, you can see, and I'm probably simplifying quite a lot here because there's a way to do this, but I'm simplifying stuff. It will take a humongous amount of time. And imagine our matrices are going to be in real life when the number of parameters and the number of neurons are going to increase, they are going to be, if you're processing images, for example, easily matrices will be 1,000 by 1,000 matrices. Can you imagine those 1,000 by 1,000 matrices ever being able to do on this? There will be a need to do how many multiplications simultaneously, how many calculations simultaneously, how many computations? 10 power 6. That is almost not almost a million operations. A million operations have to happen. That means I need a million simultaneous operations to happen. I need a million cores in order to do this multiplication, right? At one shot. I need a million cores. Can I do this? No, I can't. If I try to do this with this kind of architecture, which has only 4 cores at disposal, I'll take years to do that. And just one multiplication, believe it. And so many multiplications per layer, I'll have to do thousands of such layers I'll have to do. And imagine what will happen to me. On the contrary, if I have this, what will this architecture give me? Thousands of cores. We ourselves are having thousands of cores. In real life, companies like OpenAI, companies like Gemini, companies like Claude, or whoever, they are going to have millions of such cores at their disposal. They have arrays and arrays of A100s and H200s lined up, and they have that kind of compute power. So if you have that kind of compute power available and needed, what is the basic challenge? The basic challenge is that you somehow have to use this infrastructure in a way that suits you, that suits your problem. So you have to intelligently re-architect your naive programming to suit this, to take the benefit of this, right? The benefit of this is millions of cores or thousands of cores. Somehow, if you can do that, you can actually harness and do this calculation fast and proceed. Okay, so hopefully you have understood the first part of our solution, that is, we need humongous amount of cores. Cores means processing units available to us. Unless we have that, we will not be able to proceed. Okay, and if you are not able to do that, we have a problem. So first is get hardware, get a huge amount of hardware. And here I don't mind getting a little philosophical and telling you that this is where India has a issue, because we do not have the money to invest in such amount of hardware. 2 years ago, when Sam Walton, who is Sam Walton, the CEO of OpenAI, when he came to India 2 years ago, he was asked a question in an open forum, in a tech forum. The question asked to him was, can India create an LLM? An LLM is a program, a GPU program, AI program, which needs humongous amount of compute power, thousands and thousands of GPUs. So the answer which OpenAI gave, or Sam Walton gave to that large community of Indian tech experts was, no, India cannot make an LLM in foreseeable future. Most of our tech people thought this is a challenge, but he went on to add, he said, the challenge is not because Indians are not smart. Indians can't create software. They can, but the problem is we don't have access to such brute compute power, which is available in American universities, in American campuses, and of course, American corporations. So our effort is to buttress, the hardware infrastructure, and enhance that hardware infrastructure. Of course, we are also, have a lot of issues with the fee reimbursement and all, because this all hardware is extremely expensive to get in, and all of that. So that's why it's getting delayed, but we will have it nevertheless by next month. This kind of infrastructure, so as to put compute power. But that's the challenge, in India, we cannot do huge amount of training on our systems, on our architectures, primarily not because we have less ability to develop models, less ability to think of new models or architectural changes. I'm sure we have enough. KMIT itself, KMIT and all its other group colleges have enough power, enough intellect to do this. The problem is we don't have that infrastructure. So since the last couple of years, I've been struggling to put this infrastructure together, and now we will have it, so that we have that immense compute power. Otherwise, people use Google Colab and all such stupid platforms where it's unreliable, for development. It's okay as a toy, but unless you have this kind of a hardware available, we cannot do anything. But having the hardware available is one part of the story. We need you as engineers to understand what is it that we need to do in order to harness this hardware. Otherwise, we will have the hardware, that is, we'll have the expressway, but we'll be driving bullock carts on it. And that's precisely what we don't want to happen. We don't want it to do. And so now let me take you to the next part, after which I'll have again a poll, and say that, basically, how do we support that kind of a hardware and all that. Now, there was a question as to why can't I do more than one multiplication per core. You can, but until the first multiplication is over, the second multiplication won't start. In fact, the answer is staring at you. Even with 4 core, you can do 1,000 by 1,000 multiplication. Only thing is, it will have to be done sequential on that core, because that core can do only one multiplication at one shot, one operation at one shot, that is one row and one column. So it can do only that. And once it is done, it will wait, it will get ready to do that. But then we are introducing sequentiality to that extent. Okay. Okay. Now, given this situation, let us now talk about, how do we orient the hardware? Sorry, we have the hardware. How do we orient our software in order to do that? Okay. So I'm now going to touch upon certain ideas of how the hardware is going to influence this. How the software has to be used to harness this kind of a infrastructure or this kind of a architecture. Okay, so let me now turn my attention to look at the software which is needed to in order to harness it. How do I change the program? Okay, now, let me, I was going to delay the poll, but I'll take a poll right now. Have you understood the difference between a CPU and a GPU, and understood the importance of GPU in matrix multiplication? Or let's put it this way. Have you understood the importance of GPU in matrix multiplication without understanding the software reorganization? I'll come to that. We're going to go for a poll quickly. This poll is mainly to keep you from falling asleep also.
So I understood the importance of matrix multiplication in.
No. Question is, have you understood the relevance of GPU for matrix multiplication?
Yeah, poll has been launched. Please take the poll. 13 date date small dash second. So
Okay, we'll wait for another 2% more. The mic is off.
answer.
On. Okay, yeah. Fantastic. Okay, I think we have almost a quorum. Oh, you didn't give partly?
No, because it has to be clear, completely accurate.
Yeah, okay. I think we have 81% vote, which is what we look for. 80 is more. We look for around 80. As I said, the idea is also to keep you awake. Okay. Uh, okay. Now we have talked about at this stage the need for multiple hardware, multiple cores to be available because there are so many calculations which can be done in parallel. Now we are going to see how do we do each of these parallel operations in parallel, and I'll explain the central idea of GPU. Now this is going to be a little tricky because see normally we talk about these ideas when you are in third year where you have a course in GPUs and all that, but I think that was a luxury which your seniors had or didn't have, whatever. You guys need to understand AI from the core. In fact, the other day I was telling somebody that now the current generation has to grow up very fast, become dominized because jobs in pure computer science are gone. You will never get a job in pure computer science. They are over. That era is over. And officially, we are now going to say CSC Amar Hai. It is that kind of a time, and now is the time of CSC plus minors, CSC plus AI, sorry, CSC AI plus agriculture plus drug discovery plus robotics plus cybersecurity. Cybersecurity is also a horizontal. Plus, let's say fintech or supply chain logistics or drone or whatever. Unless you have these skills, you are of no use to society. You will never earn a single naya paisa. Just listen to me carefully. Okay, now, so you have to learn these things bottom up, whether the university wants you to do it or not. You need to do it because you need to survive and flourish. Okay, so now we have availability of multiple cores. Now, how do we reorient our software from the naive coding to a smart coding? So I'm now going to take you through a smart code for the same problem, matrix multiplication. Now, some of you will get it first shot, and some of you may take a little while to get it. Okay, but before that, can you give me a blank page? Okay, let me start with a slightly blank page. Yeah, I'm starting with a blank paper to just explain what we mean certain fundamental ideas. Okay, so GPU programming. This is the 101 of GPU programming, or what we call the basics of GPU programming. So first imagine in GPU programming, what do we have, right? We have the concept of a grid. Now, in many ways or in all ways, the grid mimics our matrix, the result matrix C. So conceptualize this. If I have a result matrix of M into N, which is what I had earlier, the C, imagine that I have a grid of M into N processing cores or cores. Cores means processing units. So can you imagine cores? Okay, just imagine a grid, okay, of 3 by 3, because 3 by 3 is our problem. This is a grid. Uh, Grid is a set of CPU cores or GPU cores, sorry. This is, each is a core. Okay? Core means a processing unit. So first of all, in GPU programming, we have to define the grid. Now you'll ask, what should be the dimensions of the grid? The dimensions of the grid is M into N, the same as your result matrix. Now, if your result matrix is very big and you don't have cores available that many, then I will tell you, not in this class, but in a later session, how we should build the grid. Okay, I'm not going to talk about it now. For today, assume that you have more than this available processors, or more than this available GPU cores. Okay, M into N, you have more than that. Okay, so let's say we are taking the problem of 3 into 3, that is a 9 core computation. Of course, there will be thousands in real life, but let's just imagine 9 cores. So there are 9 cores. So you first have to define a core. Okay, now normally, a core or a grid is divided into blocks, and blocks are divided into threads. Okay, so okay, now this is going to be a little tricky here, so I'm going to just expand the core for right now a little more. Okay, so rather than taking M into N as a 3 into 3, I'm going to take it, to make it simple, I'm going to take a 4 by 4 core. This is a 4 by 4 core. So basically I'm trying to, if you want to correlate it, I'm trying to multiply 4 into 2 matrix by a 2 into 4 matrix as an example, just to take an as an example to simplify our understanding. So how many cores do I have at my disposal? I have 16 cores, right? I have 16 cores at my disposal because I have to do 16 multiplications at the end of it. Sorry, 16 cells I have to fill, and therefore I have to do 16 multiplications, right? To get that value. Sorry, not 16, 16 into 2 multiplications. For each value, I need 2 multiplications. So 16 time values are there. So I need that. So now this whole thing, the whole thing is visualized as a grid of cores. Okay, so many cores, and the grid mimics the result matrix. So the grid is created from the set of available cores as what I need for this particular problem. Let's say there are more cores, but I have taken only 4 into 4 of those. Okay. Now grids are normally defined into divided into blocks. So typically blocks is a multiple of 2. So I'm going to take this as one block, this as another block. So each block is a 2 into 2. Okay, 2 core by 2 core. So I have divided it, and this is another core, sorry, another block, and this is another block. Okay, so my 4 by 4 core is divided into 4 2 by 2 blocks. Okay, this is my blocks. So this is first block, block 0, block 1, block 2, block 3, so on and so forth. Or we think in 2 dimensions. This is block, its x is, imagine this block itself is a coordinate. So its x will be 0, its x will be 1, and its x, if you take x here like this, it is 0 and 1. If you take y like this is x0, y0, this is x1, y0, this is x1, y0, this is x1, y1. This is, you will have to understand this. I have divided, first I am going to make again some points I'm going to repeat. I have a core which is, I have a grid which is consisting of 16 cores. Now you'll ask, why do I need 16 cores? Because my answer matrix for this computation is going to be a 16 core matrix. Okay, so that's why I need a grid of 16 cores. And the way GPU programming works is it asks for these cores to be divided, or the grid to be divided into blocks. They are multiples of 2. So that's why I have this as the first block, this as the second block, this as the third block, this as the fourth block. And see, the blocks also have coordinates. These are block coordinates. The coordinate of this block is x0, y0. The coordinate of this block is x1, y1, x1, y0. This is x1, y0. This is x1, y1. This is the block coordinates, each block. Am I right?
The top second one is x0, y1.
Oh, sorry. This is x0, y1. I'm sorry. This is x0, y1. Yeah, because this is the first row and this is the second column. So this is the way these are numbered. I'm sorry. So this is x0, y1, and this is the way the block are numbered. Okay. So they are also numbered in a Cartesian manner, imagine. So the grid is broken into block, and the block is broken into threads. So how many threads are there in every block? How many threads are there in every block? Each block has 4 threads. So my core has 60, my grid has 16 cores. The core is divided into 4 blocks. Each block has 4 cores, and each core runs 1 thread. So now you have the hierarchy: grid, block, and thread. So grid depends on my result matrix, which I want to compute. Blocks are the subdivisions of the grid into coordinates. That's how in multiples of 2. And threads are the actual working units within a block. So these are the working units in a block. So if you map it, each of these thread represents 1 core and is going to run on 1 core. So thread is actually the code which executes. So what is a thread? It is the code or the function. We call it a function. There's another name for it. The code or a function which runs on every block, which runs on every core. So every core runs a separate the same function but running 16 times. So here you see the block has 4 cores, and so it can run 4 threads, and so on. Each block can run 4 threads. Now, why is this done? This breaking of the grid into blocks and threads? Well, a block is normally an independent unit of execution, or an independent unit of scheduling, not execution. Execution all can execute parallelly, but the way internally we call it the streaming microprocessors, I will not talk about it today. At some other point, when I take you into the depths of GPU programming, I will elaborate on this at length, and we will talk about it. There I will talk about how the I'll use the word of streaming multiprocessors, how these blocks help in scheduling on these streaming multiprocessors. So at the moment, think of it as this is some kind of an requirement of the underlying architecture, that grid has to be broken into blocks, and then blocks have to be running these threads. The threads together constitute a block, and they can share memory and all of that. So there is some amount of shared memory allocated to each of these block independent, and then there is some memory which is allocated commonly. Now, each thread that runs on a block, that runs on a core is called a function, or the official name of this is called a kernel. So when we say we are going to run some code in GPU programming, we don't say we are running a function, we say we are running a kernel. What is kernel? Kernel is a code which runs on 1 core, and which basically does one part of the computation. And so how many kernels are going to run in this case simultaneously? 16. So 16 computations are going to be done simultaneously for this kind of a 4 by 4. I just expanded it from 3 by 3 so that it fits properly. Even if it is 9 by 9, 3 by 3, then also it fits, but some of the cores go waste because the allocation is done only at a block level. So some cores will be unutilized. That's why I took an example of 4 into 4. So what runs on each core is called a kernel. This can be written traditionally, kernels used to be written in C++. That is how when I was taught GPU programming, or I learned GPU programming long time ago, I basically learned it through C++, the way a kernel runs. Nowadays, in those days when I learned it, we did not have the benefit of Python. So basically nowadays we have the concept of something called PyCUDA. I'll talk about PyCUDA in a moment, where you can write the kernel in Python. This was a convenience which was not available to me when I was your age. In fact, when I was your age, GPUs didn't exist. It came when I was probably about 35 years old, when I was writing some game programs. That is when GPUs started emerging and became popular. That times there was no Python so eminent, so prevalent. And now, of course, everybody wants to write code in Python. And so there is this PyCUDA, which I'll talk about, where you can write this kernel, which is that code which runs on every thread, which means runs on every core, is called a kernel, which is run by a thread on every core. And that kernel can be written in Python nowadays. So now I'm going to show you the Python code, and I'm going to explain how that Python code works, and how it all runs. I'm going to just explain that, and if we get that understood, then we will take it forward. Okay. Okay, I'm hoping that this part is clear, and I will not do a checkpoint at this stage. I will explain how kernels are written, and after that I will explain. I think we can skip that picture. Yeah, no need. And this is a kernel, and I'll explain this kernel, and after that I'm going to pause here and talk a little bit about kernel development and kernel and GPU kernel. Now, please don't confuse this word kernel with operating systems and all, because the word kernel is used when for the operating system code, which is the device drivers and all of that. Actually, device drivers are also very close to my heart. I started my career writing them. But yeah, that is also called a kernel, but there the kernel interpretation is different. Here, kernel interpretation is the code which runs in every thread on every core. At this stage, we are going to go with a simplistic definition like that. Later, I'm going to talk about how it happens. Okay. Okay. Now, I'm going to launch into something little involved, and I will try to take about 10-15 minutes to elaborate on this. Listen to me very carefully, and hopefully we will go with a lot of satisfaction, having understood the core of GPU programming. Okay. Okay. So keep your thinking caps on, and let's walk through it. Okay. So here is a bit of Python code. Okay. Now Python, this is your NumPy library, which is gives you the arrays and all that kind of stuff. Without this, you will not be able to use arrays. So you need the NumPy, which is normally shortened to NP. So this is a numeric Python library which is needed. Okay. Now this is the numba library, which is the main algorithmic library of these machines. I'll talk about numba later, but I want right now only the CUDA part of it. Now CUDA stands for Compute Unified Device Architecture. I'll write it again. My handwriting is wrong, is bad. Compute Unified, compute, not computer, Compute Unified Device Architecture. Well, it's a big word, which means primarily the framework which NVIDIA has given. This is created by NVIDIA to enable parallel computing on its GPU cores. Okay, I'll say it again. It is a library enabled by NVIDIA. It is a some kind of a basic framework created by NVIDIA with the express objective of supporting parallel programming on its GPU cores. So that is what CUDA is all about. Okay, and it is the de facto standard. Now, typically they say if you are smart in CUDA, NVIDIA will hire you and pay you $250,000. Okay, and also probably in today's world sponsor your H1 with that $100,000. That's how expensive CUDA programmers are, and yeah, it has always been a dream that KMIT and its colleges produce these kind of engineers. But honestly speaking, over the last so many years, we have been able to produce only about 4 or 5 people who are of this level, who could write CUDA code. And we over the last 20 years, we have been able to produce only about maybe 4 or 5 people who have made that grade. So it's that tough. And typically, CUDA engineers are hired from IIT Mumbai or IIT Madras with the top of the top computer science story because it needs a bit of maturity with computer science. It needs a bit of ability to think beyond things, a lot of insights and all that. Okay, yeah, with the fond hope that we'll have some from your batch because we are starting so early, and the fact that NVIDIA is expanding, we will have some people going there. Okay. Now, this is typically one of the things which is called a decorator. Okay. Now, I'll explain what is a decorator. We call it decorator in Python. We call it annotation in other languages. Okay. This is a classic design pattern. JIT stands for just in time. Okay. I'll just spend 1 minute on this. This is a decorator, which is a suggestion to the Python as to how to look at this function. Okay. This is the kernel, which is actually a Python function. But this is an additional annotation on it or a decorator on it. What JIT stands for is just in time compilation. I will not talk too much about it. I'll just say one thing. See, Python code, normally Python is a Python is a interpreted language. That means every time Python runs, it converts each line by line into machine code and then runs it every time. Whereas when you compile something, it is converted into a compiled code once only and runs with parameters every time. So obviously compiled code is much faster than interpreted code. Interpreted means every time it has to convert it into machine code. Every time it sees the line, it will convert into machine code. Compiled means first time it sees it, it converts into machine code. And after that, it doesn't have to do this interpretation every time. It just takes this machine code and runs it with parameters. These are the parameters, right? So it runs it with those parameters. So this is obviously a faster version, much faster. Now, normally Python is an interpreted language normally. But in this case, because we want this kernel to run very fast and run on a thread on each GPU core, I am giving a special decorator to it, or ChatGPT decided to give a special decorator to it, which is called the JIT decorator. CUDA.JIT decorator. JIT stands for just in time decorator. Just in time means just in time compilation. So this code is going to be compiled, not interpreted, like whereas normal Python code is always interpreted. Line by line, it is interpreted. So this is not going to be interpreted. This is going to be compiled. So it's going to be much faster. Okay. So that is the clue we are giving here by putting this decorator or an annotation here. Okay. Now, I'm going to go and get this idea to you. I have about 10-15 minutes and hopefully you will understand this idea in a jiffy. So with all prayers on my lips and hope in my heart, I'm now going to explain to you how the kernel works. Okay. This is the kernel. The matmul is the name of the kernel. you can call it anything. This is essentially a Python function which is compiled. Okay, it's essentially a Python function. Okay, def is definition of a function and all. Now it takes, how many parameters do you see here? It takes 6 parameters, right? The 6 parameters are A, the first matrix, B, the second matrix, C, the third matrix, result matrix, which has already been zeroed out. And now the first matrix dimensions A are m into k. The second matrix dimensions are k into n, and C is m into n. Again, repeating, it has taken 6 parameters. The kernel is taken 6 parameters. Why 6? The 3 matrices. What are the 3 matrices? The 2 input matrices which ought to be multiplied, which are going to be multiplied. It is going to produce this matrix C, which is the result matrix. And now comes the dimensions of these matrices. The dimensions of the matrices are m, the number of rows in the first matrix, k, number of columns in the first matrix. The second matrix B has k rows and n columns, and the result matrix has m rows and n columns. This is what it is, right? Okay. Now I hope these parameters have been understood. Now I'm going to go to this line, and there is a lot of meaning in this line. I'm not going to talk about how this line works and all of that at this stage, but I'm going to just abstract right now that I'm asking grid for my 2-dimensional address. Okay. Let me say this again, but I'll give you a little background. So we have established already that one thread is going to run on one core, and it is going to do one row and one column multiplication. I'll repeat, one thread is going to run on one core, and it is responsible for doing only one operation on one row, one column. That is, if you visualize m and n like this is m and this is n, and this is your C. Then remember I told you it is going to take this row and this column, and this guy is going to just work on this row and this column. So every thread, every kernel which is going to run, you're going to have so many kernels running. So every thread or every kernel needs to know only one row and one column, because it's going to work only on that. It is going to multiply all the values in this row with all the values in this column and add them and produce this value. That's all it is going to do. So it needs what? One row address, this row address, this column address. That's it. And once it gets that from the grid, which is already mapped to the result matrix, it can go ahead and do it. So there is a lot happening behind the scene, but at this stage, see what the kernel is saying. The kernel is saying, or the kernel is asking the grid to give it 2-dimensional output. That is, this is 2-dimensional. It is giving, kernel is asking the grid, please tell me which cell I should operate on, which is the row and which is the column I'm going to work with. So for this kernel, the grid is going to say you work on row 1, column 1. For this cell or this kernel, it is going to say work on row 1, column 2. For this guy, it is going to say you work on row 1, column 3. I mean, I'm labeling it 1, 2, 3 and 1. I hope you get the idea. So this guy is going to work with one row, one column. This row, this thread is going to work with one. That is what is getting returned here. What should I work on? Tell me what I am going to work on. And I'm asking CUDA, give me a CUDA's grid, the grid that I established or created. I'm asking the grid, give me my 2 coordinates, give me my row, give me my column, which I'm going to work with. And the way this kernel is going to be launched and invoked, which I'll talk later, the kernel is going to be given by the grid these two values, the row value which it is going to work with and the column value which it is going to work with. That's it. And it is saying I need only that, and I'll compute this value, because that's all I need to compute this value. I don't need the rest of the matrix or the rest of the, I don't need to know anything, divide and conquer. And this guy is going to do something simultaneously, right? All of these going to happen simultaneously. So now he has his row, he has his column, then he just does a basic what you call sanity check. The row should be less than m and the column should be less than n. Obviously it will be in most cases, except a few we'll point out. Then he makes some variable 0, and then he goes range. Now he, what he's doing, he's taking this row, that is in this case he's taking all the values of this row, a row k. Is going to go with this row and column. These two are anchored, these two are fixed. The k is going to change. So the way it's going to happen is he's going to go through all these columns of this row and all these rows of this column. That's the k column. This column is fixed and this row is fixed. Is going to multiply these values with the corresponding values here and add them up. Okay. And similarly, this guy, he is going to take this row and this column and get this value as a sum of all that. And then he's going to put that row and that column. He's going to work on only that cell of C in row, column and temp. So this, what have we understood? So this column, this kernel is dedicated to only one result, one cell in the result. And for that, it needs access to one row of the first matrix and one column of the second matrix. And that's it. As long as it has that, it can do this computation and produce this value. And as long as it's producing this value, and while it is doing that, mind you, this is important, while it is doing that, another kernel is going to also run, and to him the grid is going to say, you work on row 1, column 2. And to this kernel, which is also going to launch on another GPU core simultaneously, is going to say, you work on row 1, column 3, and so on and so forth. And all of these threads are going to run in parallel, simultaneously. They are not going to wait for one to finish and then the loop to start the next one. And no, there's no loop here except the loop. There's just one for loop. From 3 for loops, we have come to 1 for loop. But that is anyway needed because you have to multiply this, all these values here with all these values here. Sorry, all these values here with all these values here to get this value, one value, right? So only one loop. Remember? So just to do that, no j, no I, like we had earlier, because it's all converted into a parallel version, right? So now these cells are going to be calculated. These threads are going to do their work. Each thread is going to launch its own kernel, and that kernel is going to get its coordinates, which are its row and its column, which it is going to work with. Extract that row, that column from these two matrices, and do the computations and produce one value only. Each thread will produce only one value of the result. Each of these threads is going to produce one value of the result. So if the result has m into n dimensions, there have to be m into n threads which are going to run from the grid, because the grid is of that size and it's going to produce those values. Okay, and I hope we have got you the central idea of the kernel and the multiplication and the parallelization and the sequentialization and a basic understanding of GPU cores, how they work and why they work the way they work. I hope at least I see now 200 people down from 250. That is the spirit of this state, and which is really wonderful that we have so less people, because in the long run there are going to be only that many jobs, right? So yeah, so this is what is the way the multiplication happens. This is how a kernel gets established and a kernel executes. And I'm now going to take a poll, and I'm going to figure out hopefully how many of you have understood the concept of a kernel, and also the basically the concept of a software kernel. Concept of a kernel. And how is a kernel written? So the poll question is, how many of you have understood the concept of a GPU kernel?
Yeah, poll is started. Please take the poll.
We are at 50-50. No, we have partly understood. Okay.
This is taking the
Okay.
77, 78, 81. I think these are the messages which have been used. So what is the difference?
What is the difference? A thread, basically, the question I have here is difference between a thread and a kernel. Well, a thread runs a kernel. So thread is a unit of scheduling, and the code which a thread runs is called a kernel. Even though software we use for Java or C uses the CPU for matrix multiplication. Yes, unless you have made provisions and use proper libraries, by default the CPU only gets engaged. You have to write the code separately. That's why when we will teach you machine learning and AI and all that, which I intend to cover in this, when we teach you tensor algebra, PyTorch and all, we'll teach you how to work with tensors. Tensors are arrays or matrices, and we will show you how to use tensors with CUDA. CUDA means GPU. Okay, so looks like the GPU kernel is not as well understood. And we will again in the next session start with this and talk a little more about it, and we'll elaborate on it. And till then, you do some reading, and we will again touch base at 10 o'clock on next Sunday and try to take this idea further. Okay. Uh, uh, I hope you are understanding largely what we are talking about. This is a complex subject, and the reason we are doing it through this series over multiple years, because this course is now engaged, it will not stop for 2 to 3 years every Sunday. It will help you in a long way. Ask your friends also to start attending because they are missing a lot. Because see, some of these concepts are covered in classrooms, some of them are not, but they are never. But it's always good to get them straight and understand. Yeah, we will upload all these sessions to KMIT Vista by tomorrow evening. Okay. Uh, by tomorrow evening, we should be able to get them.
Yeah.
Yeah, we will, because they'll have to be converted and done. Uh, is the kernel in Jupyter Notebook the same that we are talking about? Yes, kind of. And soon we'll be using Jupyter Notebook to do that. We will shift from Tessellator to Jupyter Notebook, that is Tantric, and go on. Okay, so we will put them in KMIT Vista for sure by tomorrow evening, and I will repeat some of this next session just to touch base, because a lot of people have understood partly. It's good to know that the none are empty, none are more or less empty. Uh, uh, so this will take time, believe me, because this is the heart of money making. This is where the $1 million revenues are earned. They are not going to be earned by writing some simple code. And I will also tell you, first year is the best time to start understanding this. Second year is also a bit late. Okay, just to give you an idea, see, we are going to start a university next year. Our Uppal campus is going to become a university next year. Having said that, you know what we are doing? Some of you may be aware, we also run an junior college. So in a year or so, we are going to transform the junior college as an extension of our engineering. So instead of running a 4 year engineering, we will run a 6 year engineering, because we have come to believe that 4 years is too short to become a good computer science AI engineer, especially with the domainization. And there are no jobs without domainization. That being the case, 4 years is inadequate. So we are going to make it a 6 year engineering with 2 years of our own intermediate expanded, and that's the thing. This is just to give you an understanding of how we recognize the complexity of tomorrow's engineering has to be, and what are the challenges ahead of us. Because we have done a lot of thinking, and we have come to the belief that in 4 years you can barely learn basics of computer science and be worthless. So we invest 6 years and make you far more competent and far more AI oriented. Because AI, especially when it is mixed with domain like agriculture or like DNA or like drug discovery or like supply chain logistics, it will require immense amount of energy and strength. Okay. So and time, of course. Okay. This is just to give you a heads up as to how we visualize the future of engineering. uh, and I will also tell you another thing. There is not going to be, I think, in future, computer science, mechanical, civil, electrical, all will start with computer science and then blend into each different discipline. I don't think there are going to be any more civil engineers, any more mechanical engineers. They are going to be all AI with mechanical, AI with civil, AI with structures, AI with everything else. That's going to be the new world. I think the last batches, we are seeing the last vestiges of core mechanical, core computer science, and all that kind of stuff that is disappearing. Okay, this is all my insights, which I keep giving people in the fond hope that some of it will connect. Okay, thank you. So we'll meet again next week.
Yes, thank you. That's it.